This third video of 9.3.4 deals with buffers, a very important part of the HSC syllabus because it requires knowledge of a whole lot of things. It requires knowledge of the Chatelier's principle, equilibrium, pH, and also conjugate acids and conjugate bases. And because it covers so many concepts, it's a favourite thing to ask from HSC examiners. And the basic idea about buffers is there's a few key logic steps you've got to go through. First of all, you've got to know what a buffer is. So number one, you need to know a buffer is a mixture of approximately equal amounts of a weak acid and its conjugate base, or you could say a weak base and its conjugate acid, but it's a buffer solution that contains both of those things. And because you've got a weak acid and its conjugate base, that means they'll be in equilibrium with each other, as we learned in the previous video. But also, those weak acids and weak bases are in equilibrium not just with each other, but also with the hydronium ion, which is a very important part of that equilibrium. Now, the next part relates to Le Chatelier's principle. Because it's in equilibrium, Le Chatelier's principle applies, and that position of equilibrium will shift if acid or base is added. We know if we add acids to things, we raise the hydronium ion concentration. We know if we add bases to things, we drop the hydronium ion concentration. But because hydronium is part of the equilibrium, and we know Le Chatelier's principle says the equilibrium will shift to counteract any changes made, that means if we add acid or base, all that's going to happen is the equilibrium is going to shift to try and keep the hydronium ion concentration constant. And that leads to the fourth thing. If the hydronium ion concentration is staying constant, that means the pH is staying constant because pH equals minus log of the H3O plus. So those four concepts are critical to understanding buffers, and when you write about buffers, you should make sure in a logical sequence you mention those four things. But let's go through it again now with an example to see if that helps you understand what's going on. First of all, a weak acid and its conjugate base are in equilibrium, and don't forget a buffer is a mixture of a weak acid and its conjugate base. And because they're in equilibrium, that means the Chatelier's principle applies. So let's take a case study. Let's look at this situation here where HX is the weak acid, which can, as we know, donate protons. And in this case, X minus will be the weak conjugate base. And the reason it's a conjugate base is because it can accept protons from the water. So we have HX being the weak acid and X minus being the weak conjugate base. So look at this equilibrium here and notice it's not just HX and X minus in equilibrium, there's also H2O and H3O plus. And this is the critical thing, that H3O plus is part of this equilibrium mixture. So let's see what happens. If we add acid to the system, i.e., and when we say add acid, now we know that means adding hydronium ions. By Le Chatelier's principle, what's going to happen? If we've added H3O plus, so H3O plus here has gone up. Let's get this pen right. H3O plus has gone up, or H3O plus has gone up. By Le Chatelier's principle, the equilibrium is going to shift to, let's see what happens, to the left, to consume the H3O plus. So we know from our studies of Le Chatelier's principle that if we've raised the hydronium ion concentration, it's going to try and lower the hydronium ion concentration. Therefore, the equilibrium is going to shift to the left to reduce that hydronium ion concentration. So when we're adding acid to this mixture, all that's happening is rather than H3O plus going up, which would normally lower the pH as we know, all that's happening is equilibrium shifting, keeping the hydronium ion concentration constant. And the same thing happens if you add a base. Now if you add a base, that's the same as adding hydroxide ions. But adding hydroxide ions, all they're going to be doing is reacting with the H3O plus. So when we say adding a base, yes, that is adding hydroxide ions, but effectively all we're doing is removing H3O plus. So in this situation now, all we're doing is removing the H3O plus ions. By Le Chatelier's principle, equilibrium is going to shift to, as it says there, to the right. If we've dropped the hydronium ion concentration, the system is just going to shift to the right to make more hydronium ions. So no matter what we do to this buffer system, whether we add acid to it or base to it, this equilibrium is going to keep shifting backwards and forwards to keep this H3O plus constant. And if H3O plus concentration is staying constant, therefore the pH is staying constant. Hence these things are called pH buffers. So the result is that if acid or base are added to the buffer equilibrium, the equilibrium will shift to counteract the change in hydronium ion concentration. And because pH is equal to minus the log of H3O plus, this effectively counteracts or buffers any change in the pH of the mixture. So pH equals minus log H3O plus. If the buffer system is keeping H3O plus constant, that means it's also keeping the pH constant. So buffer solutions are good at keeping the pH constant. And we've used buffer solutions in the past when we were testing our pHs of different chemicals and also testing indicator color changes. We used buffer systems so that they wouldn't change pH over a period of time. That's particularly important when carbon dioxide from the atmosphere dissolves in water, because we know carbon dioxide is an acidic non-metal oxide, and therefore if you leave a solution out for long enough, eventually it's going to become slightly acidic as it encounters the air. But if we've got a buffer solution controlling our pH, that buffer solution will buffer the changes in pH. But that's beside the point. Let's get back to this. Thus, buffer mixtures can keep the pH of a solution relatively constant. However, if you add too much acid, all the conjugate base will be converted to HX, and if you add too much base, eventually all the acid will be converted to X minus, and the buffering ability will be overcome. So here's a little example. If we've got a situation here where the buffer started off at, say, let's say it started off at this pH here. If we start adding acid, we know the pH isn't going to change very much because of the buffering effect, but it will slowly decrease after a while, and eventually when we start getting close to using up all the buffer, eventually the pH will start dropping, sort of like that. Okay, so they don't last forever. So we go back a slide. If we're adding acid to this mixture, so we're raising the hydronium ion concentration, we know we're shifting the reaction to the left, but eventually we're going to run out of X minus ions to react with the H3O+, and that's when the buffer becomes overcome. Alright, let's look at a particular example. You need to know one case study of a particular buffer in the body. And many metabolic processes only occur at specific pHs because many enzymes only function at certain pHs. The body, or your body, every animal's body, has a number of buffer systems inside the body to keep the pH constant. And two important biological buffer systems are the dihydrogen phosphate system and the carbonic acid system. I'd like you to focus on this one. This is a really good chemistry one, the dihydrogen phosphate system. And this phosphate or dihydrogen phosphate buffer system operates in the internal fluid of all cells. And this buffer system consists of the dihydrogen phosphate ions as the hydrogen ion donor or the acid, and hydrogen phosphate ions as the hydrogen ion acceptor or the base. And these two ions are in equilibrium with each other as indicated by the reaction below. So you've got H2PO4 minus plus H2O. We just said the H2PO4 minus was the acid, so it's going to donate protons to the water, and when it does, you're going to form H3O plus HPO4 2 minus. So in this case, this is our weak acid, H2PO4 minus, and this is our weak conjugate base. So there's our buffer consisting of a solution of a weak acid and its conjugate base in relatively equal amounts. Now if you add hydrogen ions to the fluid, they're going to be consumed with the reaction here. So if we add H3O plus, they're going to react with HPO4 2 minus, and it's going to shift to the left as Le Chatelet's principle says. If we add extra hydroxide ions, that's the same as dropping the H3O plus concentration, and therefore the reaction is going to shift to the right to replace those H3O plus ions. Now, cellular fluid needs to have a pH of 6.9 to 7.4 for cells to function, and this phosphate buffer is very effective at keeping the pH at approximately 7.2. And different buffer solutions can keep pHs at a range of values depending on the buffer solution you use. But that's the one that happens in our cells. Now, if you study biology, you might be interested in looking at this one here, the bicarbonate carbonic acid buffer. I don't like looking at it in Year 12 chemistry though, because it's an open system as opposed to a closed system, which we like talking about in buffer solutions and equilibrium solutions. So I really want you to focus on the hydrogen phosphate dihydrogen phosphate buffer, which is in all cells.